my experiments will do even more of the same as what the original double-slit experiment did. The original double-slit experiment kind of made the statement that this reality is not deterministic. It's not materialistic. And the reason it did that is when you put, I'll just assume people are familiar with the experiment, but when you put particles one at a time through the slits, one at a time, and there are no forces on these particles. Okay, the particle goes through the slit and it just does whatever it does. Well, Newton tells us particles travel in straight lines. If there's no force acting on them, for them to make a change in direction, a change in momentum, takes force. Okay, but there is no force on these particles. Yet these particles that are basically flying free, if you will, and pass through a slit, rearrange themselves in a diffraction pattern, which means there's some parts of the screen where they bunch up and other parts of the screen where they won't go, that they avoid. And they do this in a very specific pattern and a very specific numbers, bunch up, and then there'll be a space where they're not, and then they'll bunch up to a lesser extent in a space where they're not, and so on. It's a very precise way that they distribute themselves. Not a haphazard way, not a random way, but a very precise way with no forces to have them do that. Well, in the material world, in the clockwork universe, this can't happen. Particles don't just distribute themselves in distributions without any force being on them. So it is it's a wrench in the monkey works of materialism. It doesn't, the material world doesn't function that way. So that says that the material world is not the fundamental world. That the material world seems to be material, but at its root it is not. Because these are the particles. The particles make up the atoms, make up the molecules. The molecules make up the physical world. So at the basis of this physical world, you have particles that don't behave as material particles. Then you have to question the whole physical system is really not based in a deterministic materialism. So that's what the double-slit experiment did. And that's what made it so famous. That's why it is the big thing that started quantum mechanics in the first place. If that experiment wasn't so outrageously difficult to understand by the people of that time, then nobody would have ever heard of it. I mean, this was an experiment that was done in the early 1919, 1920, 1925. Up through that time is when these experiments were being done. Well, what other experiment do you know from that age that everybody's heard of and it's on all over the internet still? It's not old. Well, if you're a scientist or a scientist that looks at history, you know of things like the Millikan oil drop experiment that took place a long time ago, but it's not common knowledge. Double slit is a very important experiment. Now, my experiments are going to do similar things. They're going to cause things to happen that, again, will have no material cause. More dramatic things. Because though the double slit took tiny little particles that you can't see, and you're not measuring them, they're not looked at, they're just particles. Well, they're very tiny. So very tiny forces, could be at play here that we might just miss, that sort of thing. So with mine, I'm looking at things like chunks of glass in a beam splitter, okay? Or how a radioactive nucleus decays, where we measure the particle gets thrown off at that decay. And these are real physical things. They're not as amorphous, I guess, as particles. So it just makes a little stronger statement. And they're done in such a way, because they're delayed eraser experiments, they're done in such a way that the only explanation can be that it's a probabilistic reality. Probabilistic reality cannot be deterministic. Determinism and probability are, don't work together. Determinism says it is going to be this way. Probability says, it might be that way, it might not. Here are the probabilities. You see, so probability is antithetical to determinism. So, and let's say some people may argue with that if they do ensembles and clusters, but at the particle level that we're talking about, that's different. So anyway, so the only way these can be explained is that there are no particles. That particles don't really exist. There's only potential particles, possible particles, probable particles. And depending on how we measure and what we measure, those probable particles will end up in diffraction patterns or in clump patterns or someplace else. And the reason that they end up in, say, a diffraction pattern is to maintain the consistency of the virtual reality so that there is not a conflict between the physics of particles and the physics of waves. Otherwise, there's a conflict between the two, because waves are made up of photons. And photons going through slits, whether they're going through by large numbers or whether they're going through one at a time, shouldn't make any difference. It's not the crowd that makes the difference, you see. So if the particles went through one at a time and did not end up in a diffraction pattern, you would have a conflict between particle and wave physics. Well, to keep that conflict from happening, the system essentially takes its potential particles and has them array themselves according to a probability distribution. And those of you that are familiar with my work know that whenever a measurement's made, the way that measurement is made is the system takes a random draw from a probability distribution of the possibilities. And that's what happens. That's why those particles end up in that diffraction pattern, because it starts with a probability distribution that looks like a diffraction pattern, because that is in consonance. That is not in conflict with waves. That's what waves do. And then one at a time, it goes in and takes a random draw from the probability distribution of the possibilities. Okay? And wherever that comes out, then that's where it puts the particle. Wherever that random draw takes it, that's where it puts the particle. Next particle, another random draw, however that comes out, that's where it puts the particle. But you see, the system has done this to prevent an inconsistency. And that's one of my assumptions here, is that the system will always try to prevent an inconsistency in the reality. It'll want to have a kind of boundary values between, say, particle and wave as smooth, not inconsistent. So that's one of my assumptions, is that the system will try to maintain consistency. Another assumption of mine is that the system will do what's most efficient. Its math, its processes, its statistics and probability are going to be the most efficient way to get from A to B. In programming, you can get from A to B in 100 different ways, but there's only one that's the most efficient. Okay, so that's a second criteria that I've placed on it. And another criteria is that, and it's actually part of this last criteria I just mentioned, is that time is always going to move forward linearly. You're never going to have things going backward in time. A lot of people interpret the delayed erasure experiments as something going backward in time. Oh, you made a change after the fact of collecting the data, and now the data changes. So the data must have changed in arrears. The data changed after you made, that change.
Retrocausality.
Yeah, it's retrocausality. You see, and the reason they say that is you collect data on a screen, then you change whether or not you have which way data after you've already collected the data, but the data on the screen turns out to be consistent with the which way data that you've got, which you changed after you collected the data on the screen. So it looks like that screen had to change after the change in the which way data occurred, you see? Well, it doesn't work like that. It's very difficult in a simulation to go backwards in time. It creates all kinds of logical inconsistencies to run backwards in time. It just creates a problem. Can't be done. Now you can take a movie and run it backwards in time, but that's because a movie doesn't have free will in it. A movie is just a bunch of stills, right? Of actors of what they did. It's just history. It's a history of what all the actors did at what time. It's not an actual live scenario with people in it, with things in it that have free will to change. So running things backward in a live system like ours, rather than just a history book or a collection of things that are done, is very problematical. So the system will always progress. The experiment will always progress linearly in time. So what is put on that screen has to be aware of the fact that the which way data might change. And it isn't put on that screen, even the particles get there, okay? It either isn't put on that screen until after the which way data can no longer be changed, or the which way data gets changed in order to fit what's put on the screen. You see, those are two ways to accomplish that. You can say, okay, here's what went on the screen. Now the which way data is going to have to be manipulated to suit that. Or what's on the screen has to be unlooked at, unverified, unmeasured. And if it's unmeasured, you could say, well, it just is still in potential. It's not really anything on that screen yet until somebody makes a measurement of what's on that screen. There's nothing on that screen. And now after the which way data is done, now you can put something on that screen. You see, so that's one way to look at it and say that the screen, even though the particles have hit there, until somebody makes the measurement, they're not really particles. They're just potential particles. And it's only until somebody actually looks at that screen that the actual particles have to have a position. And at that time, they can change to suit the which way data. You see, that's another way of looking at the problem. Well, in my experiments, I make it such that you look at the screen always. So you can't pull that switch and say it's just potential information on that screen that can be rearranged after you figure out what the which way data is. That screen is always looked at. Every time a particle hits it, it's looked at. Every particle that gets there gets registered and it gets put in a database. A particle hit at this exact point at this exact time. And the which way data hasn't been changed yet. So we're not going to be able to say that it was just a potential particle. Now, you see, it's put the system between a rock and a hard place. The system now has to manipulate the which way data to suit what was put on the screen. Well, the which way data hasn't been done yet. How can it manipulate that? You see, that's the rock and the hard place that my experiments put the system in. What are they going to do? And we're going to find out when the experiments are done. We're going to find out. But my prediction is that they will manipulate the selection of the which way data, whether it gets erased or not erased. They will manipulate that. And they'll do that by manipulating whether things reflect or transmit at a beam splitter, or whether or not a random atomic decay erases or doesn't erase the data. You see, so that's how I'm going to be able to predict about the transmission or reflection, or about the random direction of a particle comes out of an element, because I think the system put in that situation where it can't finesse the problem is stuck, and it's going to have to do something dramatic. And changing a function that by materialism must be 50-50, you know, whether it reflects or doesn't at a beam splitter, to something that is predictable, well, that's going to be something unexpected. It's going to be completely unexpected. So that's kind of what the experiments are doing. They're taking the original double slit a step further and forcing the system to show us how it's going to solve the problem. So we won't know really how it's going to solve the problem until we do the experiment. So
well, that's going to be very exciting indeed. I like this explanation, and I know many people are looking forward to having those physics experiments done.
Yeah, those are the two kind of the big showy experiments. The other one that's also going to be very interesting, and probably the one that the most people argue about, is the one that just turns off the recorders but not the detectors. It was in the original experiments, it was number 2. I think in this little set that I'm sending out to physicists, it's probably number 1. But in any case, it's the regular double slit experiment, just a normal everyday double slit experiment with detectors detecting particles going through either slit. So a detector will detect whether it goes through slit 1 or slit 2. But that detection information, what is detected, never gets recorded. Okay, it just, the recorders are turned off, so nothing's recorded. Okay, now quantum mechanics today would claim that there is a entanglement between the detectors and the particle, and that entanglement will produce a knowledge of which slit. It'll exist in the detector. And that knowledge will then create a pattern that is just 2 clumps of data. Won't be a diffraction pattern, because the detectors indeed did detect it. They just didn't collect any information. You see? So that's the way science, that's the way quantum mechanics was said. Now, we've even had several physicists that say they wouldn't even bother with that experiment because they already know what the answer is. Okay, I'm not so sure that they know, because I can't find any experimental evidence to support it. You see, I find lots of theory that says this is the way it'll work, the way the quantum mechanics people say that it'll work. Lots of theory explaining how that works, but there's no experiment that actually shows that I could find. Well, if there's no experiment that verifies it, as far as I'm concerned, that leaves it in the realm of conjecture. It's just theory without an experiment. Now, maybe those experiments were done, 80 years ago and have never been done again because they're so trivial that nobody would bother. Possibly. But I don't think so. And the reason I don't think so is that given that this reality is consciousness-based, is a virtual reality, then virtual realities are extant, that they exist only in the minds of the players. There really is no virtual reality. In World of Warcraft, there really is no place where a bunch of little elves and barbarians and monsters run around, hiding in caves and fighting with each other. It doesn't really exist. It only exists in the minds of the players. The players get data streams They interpret the data streams as this reality, and it's a multiplayer game. So they have to see the same things, more or less. Their interpretations have to be similar because it's a multiplayer game. So if that's the case, and this is a virtual reality with people getting data streams and then interpreting them as this physical universe that we get, then nothing really comes into this virtual physical universe until data gets into the mind of a player. When a player gets the data that says there's a rock sitting here, well, now that's a rock, that's a measurement, and that rock now is in the virtual reality because a player has measured it, has gotten it, and interpreted it, you see. Until that happens, there is no rock because the only thing that creates a rock is a data stream. Now, once the system gives that data to one player and says there's a rock sitting right here on the top of this hill, now it's a multiplayer game. Every other player who looks at the top of that hill will also have to have a rock in their data stream because that's what makes it a multiplayer game. They're all playing off a similar playing field. So if one sees a rock, then they'll all see a rock. Once the rock comes into the game, it stays into the game. Okay? But if no player ever got data about a rock existing in a particular place, then that game would have no rock there. In other words, the game doesn't have rocks in it. The game only is information in the minds of the players. It's not a place where there are rocks.
And yet you have said that the data we get is as real as anything.
Yeah. Well,
any of the virtual realities we can receive data from is as real as anything.
Yes.
In other words, the dream reality, the lucid
there's nothing,
dream state.
What I say is that there's nothing more real to us than information, because information creates that rock. It was the information in a data stream that creates the rock. So there's nothing more real than information, whatever the source, whether it's our imagination or whether it's this virtual reality or whether it's a dream reality or anything else or an out-of-body experience. All of it is information that we interpret as a reality, you see. So what this has to do with the double slit is that until a player gets data in their mind, gets data sent to them that this particle exists or that this measurement exists, let's put it that way, then there is no measurement. So you see, and if there's no measurement, then it's as if there's no record of it. If it's not in a data stream, then it just doesn't exist in the reality. So the detectors are not players. The detectors are just pieces of machinery. It's a virtual detector, computed by the same server that's giving us data streams, right? That detector's in our data stream. It's a virtual detector. It's not a player. So the fact that the detector gets information is irrelevant. It's just another piece of the game, like the woods and the rock. Okay, but once that information gets recorded, now it's available to a player. Once it's available to a player, it's in the game. It suddenly becomes part of the reality. So that's why I have that experiment to determine whether or not, indeed, that's the way it works. You see, so I have all the quantum mechanics basically lined up on the other side. It says it doesn't work that way. Virtual reality would say that it should work that way. Until a player gets it, it's not in the reality. Whether another part of the virtual reality gets it or not is irrelevant. That doesn't exist. There is no virtual reality. There's only data in the minds of the players, you see. So that's why just turning the recorders off means there is no data now given to a player. There's no player that gets any information. There's just detectors and recorders, which are all virtual and all just part of the background. But no player has that information. So that's why it's important that information be made available to a person, okay, to somebody who can see it. Oh, I see a rock on top of that hill. That's information. It's been made available to somebody. Well, oh, I see a printout here that says that last particle went through slit A instead of slit B. Well, now that's information here, and that becomes part of this reality. But without that information being here, whether it was detected or not, shouldn't make any difference. So that's why I thought that just turning off the recorders should be sufficient to create a diffraction pattern. You see? And that makes me a lonely person of one versus, all the quantum mechanics, experts. And I am not a quantum mechanics expert. But it's my theory that this is a virtual reality, and that time has to move forward, and that the most efficient way it'll compute was the way chosen, and so on. It comes out with that. So we'll see. Now, I scoured the literature, and I asked some physicists who have entree to data repositories that I don't, if they could come up with any experimental evidence that just turning off the recorders would make a diffraction pattern or not. And they said no, they couldn't find any such experiment anywhere. So it's so simple, it's hard to imagine it hasn't been done. It's a very trivial experiment to do. But if I can't find an experiment that says it works the way the quantum physicists think it works, then as far as I'm concerned, that's just theory. And their theory needs a lot of help because they don't really understand how quantum mechanics works. So you take quantum theorists who say they have no idea why it works that way. You take Richard Feynman, who was one of the better quantum theorists, and he said, we'll never know why it works that way. And the mysteries of the double-slit experiment hold the key to understanding this thing, and we have no idea what those mysteries are. Well, if there's that much ignorance of the fundamentals that are in the foundation of quantum mechanics, then I'm not so quick to say, well, if that's what the quantum theorists think, then obviously that must be true. Because quantum theorists, as admitted by one of the best, Feynman, say they don't have any clue why it works the way it does. Well, with that much ignorance, let's do the experiment and see. So that's why I'm doing that. So we'll find out whether or not that indeed's true, or whether the system treats the detector like a player. I don't know that it would. That seems very problematical from the computational simplicity viewpoint. So that's how, that's where that experiment comes from. So that's kind of where all these experiments are coming from. I think they're interesting. I'm real excited to do them. But, it's not, I don't see myself as the David and Goliath, match of mythology. Little Tom Campbell, who's not a quantum theorist. I mean, when I got out of graduate school, I worked in the real world. The real world doesn't do a lot of quantum theory. Some places do, but mostly in the real world I worked in, it was all Newtonian theory. Things didn't go so fast they needed relativity, nor were they so small that they needed quantum mechanics. It was real world stuff. Yeah. So I'm not a specialist in that area, but I do seem to have a theory of virtual reality that has gotten a lot of right answers. So we'll see. But anyway, I don't see myself in a David Goliath match-off. That's not it. Science doesn't work like that. It's not that I think they'll work this way and I think I'm right and other people think they're right and we're going to find out who's right. Well, there's some of that, but that's not the main thing. Science is about finding out. It's not about being right. It's about finding out what right is. So because I don't know, I want to do the experiment to find out. And if it turns out to be different than I think, than what I would predict, then I'll learn something and that'll be good. That'll be I consider that a win. The whole point is to learn something, is to be able to take the next step. Because I kind of have my virtual reality theory of quantum mechanics to a point that I think that this is the way it should work. But if I don't have any experiments, I'm stuck there. I can't go on and take the next steps without just saying, well, I can just assume it works that way and then go on. But that's not good science. Once you get the major assumptions, you need to stop, do the experiments, and see how those assumptions work out. So me trying to rewrite quantum mechanics from virtual reality theory is kind of halted until I can get these experiments done and come to some understanding of how the system will choose to implement the virtual reality. See, how will it send us data? I could be wrong about what's the simplest way of computing. I could be wrong about whether or not they will always take time, in sequence. I could be wrong about some of my assumptions. But if I am, the only way to find out is do the experiments. So I see myself as a scientist who's come to a place where I have to make assumptions, which means it's time to do some experiments, find out how that works, and then go on. And it would be amazing. I mean, it would be nice, but it's not necessarily what I expect that I will turn out to be always right. And I just say that from a historical viewpoint. Very seldom do scientists get a totally new out-of-the-box idea, and then from there on, everything they do turns out, just the way they expect. It hardly ever works that way. The way science has always worked in the past is somebody has a bright idea, and they test it, and some of it works and some of it doesn't, so they learn from that. And then they progress the theory differently, and then they test that. And some of it works and some of it doesn't, and then they go on. And that's how theories grow, through the interaction between experiment and the theoretical part. So that's typically the way science works. So I won't be so arrogant as to say, oh, these are going to come out the way I want. Maybe they will, maybe they won't. But however they come out, it will let me take the next step in evolving my theory toward an explanation of quantum mechanics. So that's really the point of what's going on here. It's not really a me against the world. It's a let's find out. And
Absolutely.
And I'm gonna make a better theory if these don't work out. Or I might not have to make a better theory if they do work out, but in either case, it doesn't matter. It makes me understand more of where I am and how the system's going to do the rendering.
Well, I think your argument is very compelling, and I think also the fact that you understand the double slit so well, which possibly not every scientist does, so well that you can design experiments that are variations of it, speaks volumes. And I'm sure everyone who contributed to the Kickstarter campaign wants to see these experiments done. They are also very interested in what the results will be, and as any physicist should be. And I think this will add greatly to your new organization, the Center for the Unification of Science and Consciousness.
Mm-hmm.
I think it's an important stepping stone for that, and experiments such as you've so painstakingly designed should simply be done, and I'm looking forward to that, as are many people.
Yes, there's really no rationale for claiming that an experiment shouldn't be done if that experiment hasn't already been done before, right? You have to be really arrogant to come to the conclusion that an experiment shouldn't be done because you don't believe that it's going to work. That's pretty arrogant. Experiments that have never been done before, or if they have, it's been lost, need to be done again just to show how reality works. That's the point of it. So, there's a lot of people who would like to argue about these experiments, but there's really no point. Argument really isn't necessary here. In another 6 months or so, these experiments will be done. Now, we haven't yet found the physicists in the group to do it, but we're looking. We've sent out inquiries, and we are we are trying to find the right people, the right place to do these experiments. And when we do, these experiments aren't that hard. Once we find the right people, I suspect some 3 or 4 months later, they'll be done. Maybe 6 months later, they'll be done. So it'll be a while yet, but you know, these experiments aren't trivial. They take knowledgeable people that are knowledgeable of the equipment and can set it up right and do it. So it'll be a little while, but let's just wait and see how they turn out.